When we talk about Krauss representation, you should realize that it is actually quite universal, quite common, in fact. Just about any evolution of a quantum system can be expressed in terms of Krauss operators. And in particular, it may not be entirely clear to you right away that situations such as adding a quantum system, so bringing, say, system and environment together, what we call the expansion of your system to include the environment, can be actually described in terms of Krauss operators. And also the act of dropping a subsystem, so for example neglecting the environment, can be also described in terms of Krauss operator. So let me just show you how it works, simply because this will introduce the mapping of density operators from lower dimensional Hilbert spaces to density operators acting on higher dimensional Hilbert spaces. So for example, take the expansion. So if we have a quantum system in some state psi, the expansion really means that we bring another subsystem, say the environment, in some fixed state. So psi is then mapped into psi tensor E. And this operation can be written as the identity on the Hilbert space of the system tensor E acting on psi. Now when you look at this expression here, what you have here, think about this as the tensor product of. So you have the identity and you have a column vector here, but think about this column vector as a matrix which has one column. So so this is altogether a rectangular matrix which has the number of columns in this matrix is the same as the dimension of the Hilbert space associated with the system that you are expanding, but the number of rows is the product of the dimension of the Hilbert space of the system times the dimension of the Hilbert space of the environment. So this matrix, call it just V, this operator. In terms of density operators, you can rewrite this evolution of the expansion as follows. So rho goes into rho tensor projector on E. And then this can then be written as the identity tensor E acting on rho, and Hermitian conjugate of that expression here. So this thing here, so this is our operator, our matrix V, and this is V dagger. So now V is isometry. You can easily see that, right? So you can see that V dagger V is equal to identity tensor V dagger here times identity tensor E. So this is equal to identity tensor E, scalar product E with E, and that's of course is equal to the identity. So we can see that V dagger V is equal to the identity. So that's the Krauss form, right? So the expansion can be written in the Krauss form. Now a unitary evolution is explicitly written in the Krauss representation. So let me just label this part as evolve. So when we have a unitary evolution, this is explicitly written in the Krauss form because U dagger U is equal to the identity, and because this is a not only isometry but also unitary operator. So for finite dimensional Hilbert spaces we also have U dagger equal to the identity. So you see, for the isometry we only require this part, right? Now the other interesting thing to notice is that tracing can also be written as in the Krauss representation. So it's call this part reduction. So we now reduce the system. So if you take the trace of some generic row, you write it as follows. You pick up any basis So say E sub k rho E sub k. So you just simply sum over the diagonal in any basis. And you look at this expression and you look again, you can see that, well, it is already written in the Krauss form. You just have to just realize that this is your Krauss operator Ek, and this is your Krauss operator E dagger k. And because this is a proper basis, so for this basis to be complete, we require that sum over Ek dagger is equal to the identity, and that is exactly E dagger k Ek in terms of the Krauss operators. So trace is written in the Krauss representation, and the same goes for the partial trace. So if you take the partial trace, so again the let rho will be some generic density operator that is pertains to some bipartite system, and I'm just tracing over one of it, called the environment. So trace over E of rho can then be written as follows. So it's sum over k, and then I don't do anything to the system, so I put the identity tensor Ek rho, and this will be identity tensor Ek. So you see, again, this is your Krauss operator Ek, and this is your Krauss operator Ek dagger. So as you can see that the sequence, typical sequence for the evolution of an open quantum system is expand, take the system, embed it in the environment, or bring two subsystems together. So the expansion part is described by isometry, and so you can write it explicitly in terms of in the Krauss representation, where the Krauss operators is just like one Krauss operator. It's the isometric embedding, actually. The evolution proper, when you bring the two subsystems, the real proper evolution of the quantum system is this unitary evolution. We don't have any other evolution really in quantum physics. So that's also explicitly written now in the Krauss representation. So the Krauss operator is your unitary matrix here. And then finally, reduction, when you just drop part of the system. So you just say, okay, well, now I'm only interested in this particular subsystem, so I trace over everything else. Call this everything else the environment. So tracing is also explicitly almost written in the Krauss form, and that includes also partial trace. So that partial trace, that is what we are really interested in. So that operation. So now any evolution, any physically admissible evolution where you just combine two subsystems, so you do the expansion, you evolve, and then you just drop one of the subsystem, can be then expressed as a Krauss in the Krauss representation, simply because we know that the concatenation or composition of operations that admit Krauss representation is also an operation that admits Krauss representation. So one can postulate that any evolution of an open quantum system can be understood in terms of this sequence: expand, bring another subsystem, evolve, a proper unitary evolution, reduce, forget about part of the system. And so clearly this is all nicely expressed in the Krauss representation.